Okay. So today we are going to look at the negative characteristics, and that will be the and an application of those negative characteristics. Today's date is 16th. Okay. Okay. So I am going to look at the or negative is not good. Okay, we are going to look at the reverse bias characteristics. So just to start, let's go back to the graph that we had. Okay. So I am not going to draw the forward characteristic, because if you draw the forward characteristic, then you cannot draw the negative characteristic showing enough information on the same scale, right? Because the negative characteristic currents before breakdown are of the order of picoamps or nanoamps, whereas the forward characteristic currents are of the order of milliamps, right? This is before breakdown. But what we are going to do is to look at the device once it has broken down. Okay. So basically you have a characteristic for the negative bias, which is something like that, it goes like that and then like that. Okay. So I am not drawing the forward characteristics, just to keep things precise. This is still a diode drawn so, right, and I am plotting the voltage across the diode, and the positive sense of the voltage is at the anode, right? This is the anode, this is the cathode, and that's the current. Okay. So what do you think is this value roughly? Right? According to the exponential model that we had, what is this value? Minus Is. Okay. But if you see here, if only minus Is, it will be absolutely flat, right? But in a more realistic diode, right, it will not be exactly minus Is. There will be a slight change as a function of voltage, and that's why it's drawn like this. Okay. Then we will look at why these things happen in the next course. Let overwhelm you with device details in this course. Our intention now is to actually design a circuit using this. Okay. Then you can talk of a voltage here and a corresponding current. Okay. This is called the knee voltage. So I call this as minus V knee. When I am putting the negative sign will become evident soon. Okay. And this is your minus I knee. At that voltage, you see that the characteristic changes significantly, right? From this very low current, it changes into this almost vertical line. Yes, come. Okay. So just as for the forward bias, we had defined something called an I test, right? And then we had defined the cut-in voltage based on that I test. Similarly, you can define something like call that as IZ test. Okay, and correspond that you can have a minus Vz. Okay, the Z refers to the fact many of these diodes are called as Zener diodes. So now it's important you keep one small issue in mind. The Zener diode is a diode which is designed to work in its breakdown mode. Okay, and as I mentioned earlier, there are two kinds of breakdown. One is called Zener breakdown, another is called avalanche breakdown. But both these diodes in common usage are referred to as Zener diodes. Okay, so that's bad nomenclature, but that's the way. We won't worry about that in this course. The difference in the mechanism of breakdown. The Zener breakdown refers to breakdown with tunneling. Avalanche breakdown refers to a process wherein you have the creation of an electron hole avalanche. Okay, we'll explain these things in detail in the next course. Let's not spend now here. Okay. So, how do you approximate this? Right? Yes, a resistor is one approximation, but the simplest approximation for this is to that I am going to basically have zero current all the way up here, okay, and then current like that. All right, that's simplest approximation that you can do, and we will design circuits using this simple approximation. All right, only thing you have to mind is that for this device to actually operate, your current should be in the negative sense more than INE. If less than INE, your device will not really operate well. So when you design your circuit, you will ensure that the current is more than INE, its negative sense. Similarly, there will be some current which is say sinus IZ, which is about the maximum current that device can handle. So when you design a circuit, you would want to ensure that the current in the negative sense passing through the device is less than IZ max, because otherwise the device will burn out. So this INE. So what are the typical design, the specifications for this device? Your INE is an important specification, your Imax at max is an important specification, and your EZ is an important specification. So if you go to the circuit, you will get Zener diodes which have a Zener voltage VZ of say 6 volts, right, or 7 volts or 3 volts. So you decide what power supply you are making, and then you go to the market and purchase the appropriate Zener. Also, you would have to ensure that the amount of power that your power supply is displaying is less than the rated power handling capacity of Zener diode, so that burn the diode down. Okay, that's what we will see now. All right. Any questions? Okay. Just to complete this, just as here we have drawn a vertical approximation for the the red line has some slope, but I have approximated it with a vertical line, right? So that red line has some slope, and define a resistance for that. In a more advanced calculation, you might want to use that. Typically, you don't really care. Okay, you would see that when you are designing circuits, you can actually design things with very crude models, and it will be instructive once we do a SPICE class that you take the more realistic model and then check your and compare it with what you have obtained using hand calculation, using a very crude design, and you will find that you are not too badly off. So design is very different from analysis, and that thing that you have to keep in mind. Okay, all right. So now let's go to applications. Now, before we go to the application of a reverse bias diode, let's just follow. Okay, say I have the following situation where I take I've drawn 3 diodes here. In general, let me consider, and I pass some current through this. Okay, say that I have in general N diodes, all of them forward bias. Okay, if they are real diodes, then what would be? What can you this voltage as? Let me not assume it's a real diode. Let me say it is a the V gamma from R of model. Okay, piecewise linear model. Assume that you are working with this kind of. Then what would your voltage be? Right. So you will have an N times V gamma. right? So you can actually draw this a battery with NV gamma and correct, right? This would be N. What is your magnitude for D? How to work out RD2 last time? Very roughly. Right? It will be of the order of some tens of ohms. Right? So it's going to be some ohms. So this, depending on what the value of N is, it will N into that. Right? So if you say you want a 6 volt type, right, and say V gamma is 0.6, you will have 10 diodes connect, all of them forward biased. So you get 10 into 6, which is 6, and your resistance would be 10 into, so this is tens of ohms, so assume this is like 20 ohms, right? This will be 10 times that. So what's happening is that if you fairly large voltage, the series resistance that is along with this thing is actually also increasing. Okay, so the take home point is that the series resistance scales in this series resistance. So this is for case of a forward biased voltage reference. A battery is a voltage reference, right? Reference. So overcoming this is actually to use the reverse bias characteristic, because in the reverse bias characteristic you can get a Zener, right? You can get a Zener of 6 volts. You can get a Zener of 6 volts. In which case you only will deal one resistance corresponding to the slope of the reverse breakdown, and that will be also order of tens of ohms. So you to at least eliminate the scaling by n issue that you. Okay. Why do you need a regulator? So the application that we are actually going to look at is called a shunt regulator. So we had looked at supplies, right? We looked at a power supply where you had some transformer, and then you either wave or half wave or whatever. So I'm not bothered. Let me just draw the half shelf over here, right? And then I had connected my load, right? And I had connected my capacitor here, and I found that the out at this point was really good, but it had some ripple, and you calculate the ripple factor. However, is there any guarantee that this output voltage will be fixed to any certain? Say I want to make a 6 volt battery charger. Can I guarantee that this output voltage will always be? Why? Okay, that's all right. I am willing to live with some fluctuations. I am willing to live with a ripple. Can I guarantee into the ripple, right? Can I guarantee that will be around 6 volts? Okay, what is the value of the peak that develops in a half rectifier? What is it related? So if I assume that this is an n:1 kind of transformer, okay, and I call this say V sin omega t, then what is this DC value roughly? The voltage across the capacitor, Vp by n, right? All the ripple and everything comes over this, but the DC value, right, is roughly D by n. What happens if the voltage that's coming in? So say this is your sinusoid that you're in the mains. Say this, instead of 220 volt RMS, fluctuates between say 180 RMS, say 240. So say your input say 1 volt RMS to 240 volt. That is not really unusual, right? For a long time many of you were cribbing that the hostel the voltage was fluctuating, right? And it's a fact of life, right? We could rectify the fault, but many times it's very hard to rectify the fault and you will see fluctuations. Even now if you go back and see, you will have some fluctuation, just that it's not as horrible as it was when you complained, right? So however, you want your battery charger to be 6 volts irrespective of what the input is. And it's possible because your input is fluctuating from 180 to 240, right? It should not be that difficult for you to come up with a circuit that gives you a fixed input voltage, correct? And that is the motivation of a regulator. So a power supply, as we discussed very long ago when we started designing power supplies, right, has a step down. We have discussed the step down. Has a rectifier block. We have discussed many kinds of rectifier blocks. We discussed the half wave rectifier. We discussed the full rectifier with center tap. We discussed the full wave rectifier with a bridge configuration, right? Subsequently, there is a filter, and we just motivated the filter in a slightly different way by talking a capacitor and then looking at that capacitor as peak detector. But in a sense, that R and the C forms a filter, right? That filters out a lot of the higher frequency components and leaves you with something that looks like a DC. Then the next bit, what we have drawn here also is like a DC with ripple, right? Then subsequently I want to send it through a regulator, then give you a good fairly constant voltage. Alright, so that's the bit we are looking at. That's the context. Okay, so what do you think you do? So you basically have a DC voltage, right, which is fluctuating. So what can you do? Keeping in mind that we have already motivated the Zener, can you come up with a simple circuit that will regulate the input voltage, or rather regulate the output voltage? So what I am interested in is to take this VDC, right? I want to take this VDC and pass it through and get an out. So the input itself can fluctuate, say from V in min to V in max. This is a D voltage which is fluctuating in the range V in min to V in max. I want to be able to regulate this and give nice V out. That's the motive of this regulator, right? The motivation is clear with all right. So what do you do for that? Right, that's one. You've hit the nail on the head. But basically, if you take a battery, the voltage across a battery is fixed, right? So drawn here, for example, in this particular situation, right? This combination of forward bias diodes is acting like a battery with a small resistance, and I just motivated that instead of using the forward bias diodes, you can actually use a reverse bias diode also, and the advantage that configuration is that this resistance is going to be much smaller. So we'll take the ideal case where this resistance is basically 0. Okay, so let's do that. So say I have an input voltage which is varying. Okay. I'm going to put a block. I'm going to tell you what it is. We'll do that. And say I connect a Zener diode. The Zener diode itself is drawn with this funny symbol. So the cathode in a diode, regular diode, is drawn by a line, right? So instead of just a straight line, you have this line which looks a Z. So that is a Zener diode. Nothing. Just some interesting person thought, okay, Zener diode, let me put a Z there. Right? You have to come up with some kind of symbol, no? Someone else may think, let's put something with a party hat on it and call that a Zener diode. Also okay. Right? Something. It's a standard acted symbol in textbooks, in many articles. Somewhere else, somebody else might have a kind of nomenclature. You'll have to go with that, right? Okay. So now you want to connect your load. So the load, will be disconnected out from here, right? I don't want to connect the load here. You have the capacitor, then after capacitor you take the regulator and then you put the load. That's the small change that you will have. Like the situation. Where is that? I went right. Right? The load will come. The load come after the regulator. Alright? Okay, I will let you guys also flip back. Alright. Okay, so I mentioned that there is a rating the IZ max. Okay, and then I also mentioned everything was put with a negative sign. The reason everything was put with a negative sign is that in its standard operation, right? In its standard operation, I am giving in a V in over here which is going to fluctuate. But the V in is drawn such that the positive terminal is actually going to the cathode. Right? So that's why now the current that is flowing through this device, the maximum current that can flow through this device is going to be, it will just be IZ max. Right? However, you draw it on, when you draw it, you have drawn this as minus IZ max, so that current that flows through the device, the maximum is going to be IZ max. Okay. Now I limit the current through this Zener to always be IZ max. So what do? You have to put a resistance, right? So this block here, which I did not draw, is some resistance. Let me call that RS. Okay. So you can, for example, decide that V in divided by RS, right, is going to be the maximum, or not, sorry, it's not V in divided, it is V in minus Vz divided by R, right, because the voltage over here, this voltage is always Vz. And if I assume that diode has this nice vertical characteristic, then the voltage does not change irrespective of what current flows through the device. Only thing you have to ensure is that the current through the device should be greater than I, less than IZ max. That's your design, right? Very straightforward. Basically, you have to design such that for whatever specifications the user wants, the current through the Zener is limited between I and IZ max, so that your voltage is fairly constant and equal to Vz. Okay. All right. And now your load connects. Load connects there. Okay. So what are the parameters that you have to do things here? What are the parameters that you have? V in, do you know? Can you control V in? No, right? That's dependent on the power supply. So V in is not a design parameter. Can you control RL? No, right? Because the user may tell you that I want a power that can draw up to say 100 milliamps. Right? Can provide up to 100 milliamps. Right? So RL is also not under your control. What is under your control? Right? RS is under your control. VZ also the user is going to tell you. User tells you that I want a 6 volt charger or a 12 volt charger. Right? So VZ is also not under your control. So under your control is RS. So you have to design RS. That's what we have to do. Okay. So let's start with an example so it will motivate you in a better way. So let me say that I want a related supply of 6 volts for load current in range of 1 milliamp to 20 milliamps. Okay. Say input is from 10 to 15. Okay, so that Z ni is equal to 0.1 milliamps and your IZ max say is 50 milliamps. So the value of IZ ni IZ knee, IZ max at 6 volts basically sets the Zener diode. Right? So you have been told to use this Zener diode, right? And so now you have to design stuff. What you have is the choice of RS. Okay. So how would you go about this design? So let me call this current as IZ and let me call this as IL. The current through the is IZ, current through the load is I, and current through this resistance, let that be IS. Okay. So can you tell me what is IZ minimum? Why do I want IZ minimum? So this I minimum must be greater than I need. So your basically what I am saying is, for all the things that are being in this circuit, you can calculate what is the global IZ minimum, and that IZ minimum greater than the I need. Similarly, for all the things that are varying in the circuit, right? What are the things that are varying in the circuit? Right? Yes, you have to choose, right? Your Vin is varying, your RS is also varying, load is also varying, right? Corresponding to your load current ranging from 1 milliamp to 20 milliamps, your load resistance is also varying, correct? So your IZ minimum must be greater than IZ, and similarly your I. Okay, this is a bad nomenclature because this is bad nomenclature. So let's call this as IZ. Okay, let me just call that I. Okay, so minimum must be greater than IZ knee, and I maximum must be less than IZ max. Okay, otherwise I would have confused if you were saying Z max less than IZ max, which is not good. Okay, so it makes sense, right? So now can you tell what I minimum will be? Or we can start in a cleaner way by first writing what I is. What is I minus IL? Okay. So if you want I minimum, right? Both IS is changing and IL is also changing, right? You can think of a general situation where IS is changing and IL is changing. So in that situation, I minimum be, it will be IS minimum minus L minimum. So I am wrong there. Good, right? So all of you are awake. So this IS minimum minus IL maximum. Correct? So you take the minimum of the first number and the minimum of the last, you find that difference, that will be the minimum current flowing through IZ. Similarly, what I max will be IS max minus IL minimum. Okay? So what is IS itself? It's minus Z divided by R. Okay. Here IS. Okay. So now just have to put in the numbers, right? For I minimum, let's now just calculate values. I minimum will be V in minimum, correct? So V in minimum, what's your V in minimum? 10 volts. Minus, what's your VZ? 6 volts. Divided by RS, you don't know. Okay, assume RS is varying for some reason, right? Let's just keep this like an RS max. Right? Minus IL max. And what is IL max? You already know, I have already told you. IZ max is 50 milliamps, right? No, sorry, 20 milliamps. Okay, I max, right? This is 20 milliamps. 20 milliamps, right? And this whole thing must be greater than 0.1 milliamps. What does this give you? Just rearrange everything. Can you work out RS max should be? Should be less than or greater than, check. Less than about 0.2 kilo ohms, around 200 ohms, right? If you do it correctly, it will work out to 199 ohms, right? Good. Correct? And everyone got this? And similarly, I can find out what for I max. I go to I max, and max will appear when Vn is at its highest value. It's the highest of Vn 15. So 15 minus 6 divided by S should be min or max? Min, right? I haven't told you yet why I am RS max, but it will become clear as I now when I finish the. Okay, so let me just put this as R min. Minus, what's your IL max? Sorry, what's your IL min? 1 milliamp. That must be maximum cut through the 50 milliamps. Correct? So when you calculate what RS min must be greater than equal to. Good? Yeah, I'll tell you why. Yeah, you can. Yeah, you can actually just. Yeah, that's also valid. You don't need to put S min and RS max. Just put RS. That's also allowed. Okay, there's no problem. Okay, yeah, that's cleaner. Let me not confuse you unnecessarily. Okay, so let's remove this max and min here. Right? You're basically trying to get a relationship for RS, right? So you can just choose. You don't need an RS min and RS max. It's just confusing you. Okay, so basically, from these two, you have a relationship that 176 ohms less RS less than to 199 ohms. What's the value of RS you can choose? 180. Why do you choose 180? Exactly. So Prasanna has the answer. 180 ohms is easily available in the market. Okay. If you look at the values of resistances that you get, have a look at that. It's very interesting to see that. They don't give you all values. It's actually in kind of a logarithmic range. Okay. So 3.3, they'll give you 2.2, there's a 2, there's a 1.8, 1.5, right? There's a 1. But if you 0.3, it's not available, right? So you want a resistance which is easily available. And 180 ohms is an easily available resistance that you can choose. Okay. So 180 sets the value of RS. Is that enough to specify the value of RS, or is there something else you have to worry? What are the specifics of a resistor? Exactly. Or in other words, related to the current, what's a better rating for a resistor? Power, right? So you have the thin resistors that you used last time. Those are quarter watt resistors. If you go to higher rating, you get a half watt resistor. Then you will get like a watt resistor. And then if you want to, if you're designing like a fan regulator or something, the old fan regulators which are really big, those would have been like 10 resistors, right? Nice and thick and fat. So you can't take a quarter watt resistor and put in an application which requires 10 watt of rating. What will happen? It will burn, right? You don't want that to happen. Fire hazard. So to specify a resistor, you need to specify its value and also its power. So what would be its power rating? The power rating, right? you so basically find out what is the maximum current, right, and work with that, or you can find out the maximum voltage and work with that also. What's the maximum voltage across the resistor? The maximum voltage across the resistor is, so I can call that Vs max squared divided Rs. Vs max 9 volts, right? When Vz is at its maximum, when V at its maximum and Z is at 6 volts, so 15 minus 6, which is 9. 9 squared is 81. So that is 9 squared divided by 180. What is this? 0.5. Choose. When you can buy 0.45 watt resistor in the market, you can, right? So you can choose a half resistor, but I won't be really happy choosing a half watt resistor. I may go with a 1 watt resistor, right? Because half watt is too close for comfort. Give it some factor of safety and just buy a watt resistor and work with it. Now, just as an aside, only have half resistors and I want to make a watt resistor. What can you do? Right? If you put it in parallel, per rating will add. So say I want a final resistance of 180. I can take a 360 ohm half and another 360 ohm half watt, connect them in parallel. Their final resistance value 180 ohms and their power rating will be 1 watt, because each of those resistors handle half a watt. So in total combination can handle 1 watt. Okay. So this basically completes the design of VZ. This particular regulator, as mentioned, is called a shunt regulator. Why is it called a shunt regulator? Huh? No, what's a shunt? In parallel. So what is this regulator doing? Exactly. So the regulator is eating away as much current is required so that IL into RL is always equal to volts. Any difference in current is going through the Zener, subject to the fact that that difference is between IZ knee and IZ max. Okay. Now just finish this story. I want to draw the quiescent point for this particular circuit. Where will the quiescent point appear for this circuit? Do you think the quiescent point will appear for this circuit? I want to draw the load line. All of you are familiar with load lines, right? We did a lot of it last semester. So, where do you think the load line will appear? Will it be in the first quadrant or third quadrant? Well, I have drawn it suggestively. Third quadrant. Why is that? Because the voltage here is the voltage across. This is the anode and cathode, right? This voltage V is the voltage drop. Sorry. Is that voltage, right? This. That's that voltage. However, the voltage that are appearing in your circuit are the new of that. So, to just fix this, that's your IS. How do you draw the load lines? Let me draw it and then let's see if it makes sense. Okay. Can you tell me the limits are here? What is this value? It will be V, yeah, right? It will be minus V in minus Vz. Assume now this V in is not changing, right? Assume it's a fixed value. So it will be minus V in. What does this line represent? Right? What is line represent? Right? So you are basically trying to run expression for small v. Small v is the extra volt is minus Vz. You can write out Vz as equal to in minus IS, right? Which means that your minus V equal to in, and IS is nothing but so no, let me take this for example as minus IS. So basically this will be minus V in, and this value, just think about this and see this again tomorrow if there is some confusion. This value will be minus V in divided by RS. Okay. Actually, okay, I think that's why things are looking confusing. For this particular load line, let's assume this is not there. Okay. So this is just, okay, assume that this is not there, then it is clean, right? Is there confusing you? So assume that is not there, right? This is just the load line for the Zener mode operation. We have done the load line for the forward mode of operation. This is just the load line for the Zener mode of operation. Don't connect it to the shunt regulator we discussed in the previous page, right? If you put that, then it becomes more complicated. Without that, it's straightforward. If you want to put that, then you have to take that RL, and that will also come in parallel with the RS and become little complex. You can do it. Basically, you have to find an equivalent and Thevenin voltage looking from the diode, right? And then that will give you this line. Now, in order to avoid all that, I just wrote out the load resistance. So it's clean, right? So this quantity, right? Quantity is nothing but your small I, right? So if you now apply everything with a negative sign, I will get V equal to minus V in, right? I times RS. Minus I times RS. Right? And then you calculate the situation you have when you have I 0, then when you have the situation V equal to 0. It will give you these points. Okay. So that's basic the load line for the Zener mode of operation. Okay, just keep in mind. It is useful to have in. Okay, so just to summarize all that we have done so far from the beginning of the course, we started off with Bode plot, you forget. Okay, so we started off with an ideal diode, then we looked at a ballistic diode, we looked at then equivalent circuits for the forward mode of operation. We discussed a few equivalent circuits. In the tutorial, I asked you to calculate the same circuit with different equivalent circuits and see what the difference is. Okay, and you will use Python in one of those things because you have to do something newly. Then we had the small signal equivalent for the forward mode of operation. Then we went into many applications. We looked at rectifiers, half wave, full wave. We looked at peak detectors, clamping circuits, voltage doublers. Tutorial, you have a voltage multiplier. I won't tell you which circuit it is, but there is a voltage multiplier there. It's a fun circuit to analyze. Okay, in fact, somebody said you can rig it up and then maybe you can kill a few mosquitoes. Okay, then another application is AM demodulation. We didn't finish this. It's again there in tutorial. Then we did some diode shape networks, right? And Prakhar had asked me in this thing where trying to shape a triangle into a sign. No, the red line is not really looking like a sign. So in the tutorial, I have something that looks more like a sign, right? So you will work out one more segment in this linear approximation. Then we did a clipper, but I didn't finish it. It's again there in your tutorial. Okay. Then we spent a lot of time on DC power supplies, looking at how to design the various components that go into a half wave rectifier based DC power supply, and then in a full wave rectifier based DC power supply. We didn't do the kit design, but I'm sure that you can do it there in your tutorial. And finally, the reverse bias characteristics and one application, which is the shunt regulator, and we discussed how you should design VZ for this